In this problem, we're looking at a qualitative variable, in this case color, and looking at what percentage of samples would have that color. Specifically, this uses the central limit theorem and the normal approximation to the binomial to come up with some parameters for this bell curve that will help us make predictions and calculate probabilities with regard to the sample proportion. So the sample proportion is the number of observations out of the total, or basically what percent of the sample meets a certain criterion. Here we're looking at what percent of the sample are born green. Now out of a sample of 123, we would take that sample, observe how many are green, that would be our x, and then x divided by 123 would give us a sample proportion. If we did that over and over and over again for every possible sample of 123 newts, obviously that would take a very long time, but we would get some very predictable results. The central limit theorem tells us that we would have just as many samples with the percent below 45 as above, and it would be symmetrical. We can also predict how much variation we'll see by percentage using this central limit theorem, normal approximation to the binomial, essentially this formula we have right here. So just to unpack these variables in the formula, what we see here is a mu subscript p hat. That's saying the average sample proportion, and that equals p, which is the population proportion. In our problem, we had a population proportion of 45%, or 0.45, so we'll put in 0.45 as our central value. Now, one unfortunate thing with the coding here is that we can't see that entire result after we type it. It might actually be better to leave out the 0 in front. So according to our formula, if the population percent was 45%, then the average percent of all the percents is still 45%. The second one is the standard deviation of sample proportions. We usually just call it standard error. And the standard error is just standard deviation for a sampling distribution. So it tells us, when we say standard error, it tells us that we're comparing sample to sample. And standard error or standard deviation, it's always the distance from the center of the curve to the inflection point, either side, left or right, which is the flat side of that curve. So we see kind of like this concave curve on top, and then convex on bottom, or sort of more open than closed. And then somewhere in between, it switches that concavity or switches that curvature. That's a calculus concept called the inflection point. And so we could stretch this or shrink this, but the important thing is knowing how big is that distance. Is it a 2% standard error or a 10% standard error? That will change depending on something like mostly how big our sample is, n, but the p and 1 minus p can affect it a little bit. So if it's a 50-50 split versus a 90-10 split, we get a difference there. And the bigger factor there is the sample size. A larger sample size, you'll divide by a bigger number, getting a smaller result, meaning a nice and tidy distribution with less variation from sample to sample. So that should make sense. If we quadruple the sample size, we have a lot more information. We should have a more reliable calculation. Now to finish this problem, I need to calculate that standard error, and then I need to add it twice to the center value and subtract it twice. It says to round the final answer to, here it is, 2 decimal places. So we'll want to keep that in mind, but it's best to do that rounding at the very end, just to keep the precision going all the way to the end. So to do this problem, first I'm just going to build that standard error formula. That was square root of p times 1 minus p. So that's 45% and 55%. If you want to do 0.45 and 0.55, I'll type it in fully here, skipping the mental steps. So there's p times 1 minus p, and now I'll divide by n. Mine was 123, giving me a standard error of about 4 or 4.5%. I want to keep that full precision and now start with that mean value, which is our population proportion, and I'll add 2 of these, so 2 times, and now I can just copy and paste that whole expression. And again, copying and pasting and just changing it to a minus 2 times that standard error. So this is the population proportion plus 2 standard errors and minus 2 standard errors, giving me 54% and 36%. So 0.36 on the left, 0.54 on the right. And we'll just double check it, but the only other issue you might notice is, and I'm getting rid of those zeros in front so I can see the numbers in the boxes. The only other issue that you might have, some problems may have been created with less precision. So if you're ever doing a problem, getting it wrong, and you feel like you're really doing a great job, reduce the precision a little bit and see if that fixes the problem. For example, here, if I did rounding initially, then I could change this to a 0.04, and I would have a less precise final answer, but unfortunately, a lot of people do this kind of shortcut. So it's something to check if you're not getting it right. Downgrade the precision a little bit. It's the last thing we want to do. But with these homework problems, this is all open source material, so sometimes there are little errors like that.